Hi everyone, my name is Luis Felipe Cadena, and today I will talk about the Rubble Zone Below Salt, identification and best drilling practices. Drilling subsalt rubble zones can be challenging. For this reason, a joint industry project from 2005 to 2009 involved acquiring, analyzing and documenting more than 100 subsalt wells in the Gulf of Mexico. The result of this study culminated in the compilation of a large database of petrophysical, geophysical, and drilling data. This database was used to develop a set of suggestive best practices for pore pressure estimation below and around the salt bodies. This study presents the diagnostic criteria for a subsalt rubble zone and several other confirmatory criteria. This study documents current industry methods for drilling subsalt well based on analysis and multiple sources of data. During the process, data from a significant number of subsalt wells was acquired. In this figure, we can see the subsalt wells location in the study. A total of 107 wells were publicly available at the time of the study, and 15 additional proprietary wells were analyzed and included in the statistical analysis. The data included but was not limited to logs, drilling records, and seismic data. The wells in the database derive from different geographic locations in the Gulf of Mexico. Rubble Zone Below Salt. Literature about salt frequently labels the sediments adjacent to salt using different terms, such as shear zone, smear zone, gulch zone, drag zone, and rubble zone. For consistency, the altered sediments are divided into two sections. The shear zone is comprised of sediments immediately adjacent to salt. The zone is characterized by highly smeared or sheared sediment, highly plastic, exhibiting gumball-like behavior. Attributed to high shearing forces, the sediment can be at or near the pore collapse state. The effect of pore structure destruction on pore structure or pore pressure is responsible for needle margin drilling. The sediment can have high pore pressure at a near mean steady state. The second is the rubble zone. This is comprised of sediment that is comparent. Older sediment having been disturbed by salt movement, resulting in fracturing. As a result of extensive fracturing, drilling fluid losses can occur, and these sediments that are less affected by salt stress and are not different to the level of a pore collapse state. Rubble zone identification correlation. An analysis of the wells in the subsalt indicated that the majority exhibit some evidence of subsalt gulch or rubble zone. A total of 87 wells contain sufficient data for this analysis. The others were missing data. Of these wells with data, 39 have a clear indication of a gulch or rubble zone below the salt. There is a correlation between the location of the wells and the presence of the subsalt gulch or rubble zone. Gulch zones are more commonly found below inclined feeder channels and below salt wells or near wells that in order structure configurations. Sub-canopy sediments have a gulch zone 66% of the time, about the same as the overall occurrence of gulch zones in all wells. The next is criteria for identification. The diagnostic observation made for subsalt rubble zone is a discordance between the gamma ray and resistivity logs in the interval immediately below the salt. This figure shows an example of a subsalt gauge or rubble zone from well EB170. This well meets most of diagnostic criteria for possessing a gauge zone. The rubble zone identification criteria are the first is gamma ray and resistivity discordance. The logs appear not to be synchronized, and in this figure, this thickness interval of discordance is 250 feet below the salt. The second is washout caliper data. Sometimes there is a washout sum in the caliper data that can identify instability within this gauge zone. Gamma ray charters. Some of the wells have charters of varying values within the gauge zone. Resistivity charter. Some degree of charter exists in the resistivity data in 22 of the wells where a gauge zone is definite. The next is the anomalous sonic. The sonic log data, when available, occasionally reveals an anomalous low value within this interval. The next figure shows an example of a gauge zone identification where only a gamma ray and resistivity log are available. Here, the identification is based solely on the discordance between the gamma ray and resistivity log in a 230 feet interval below the salt, supported by the presence the above gamma ray and resistivity charters. A thinner gauge zone is shown in this figure. It's only 80 feet thick, but we can see the discordance between the gamma ray and resistivity data. Gamma ray and resistivity charters and anomalous sonic log and high gas reading, which all the within this interval immediately below the salt. A thinner gauge zone is shown in this figure. It's only 80 feet thick, but we can see the discordance between the gamma ray and resistivity data. Gamma ray and resistivity charters and anomalous sonic log and high gas reading, which all the within this interval immediately below the salt. In the next figure, we can see a well with no apparent gauge or rubble zone. None of the criteria that have been identified are present. The gamma ray and resistivity logs are synchronized immediately below the salt. If there is a gauge zone, it would have a thickness of 20 feet or less. Rubble zone drilling practice and hazards. In the rubble zone, severe drilling losses or kicks, as well as wellbore instabilities, can occur. Circulation losses are by far the most expensive and frequently uses that occur in the subsalt rubble zone. The main cause of problems encountered when drilling the rubble zone below the salt is the narrow drilling window. Poor and fracture pressure prediction below the salt remains a complex problem. Mud weight at salt exit. Mud weight designed for salt exit is critical to well success. With careful controlled drilling, if the kicks influx volume is minimized and it's removed in the relatively design. The sun mud weight required to drill below the salt is based on many factors, including wellbore stability requirement for the sediments below the salt, wellbore exit angle and azimuth relative to salt sediments behind angle, stress perturbation below the salt and its impact on the sediments, pore pressure and strict, and the last lithification state of sediments before that movement. Casing settings. Several approaches are used to casing near the rubble zone. There are two approaches. The first approach is to drill through the salt and rubble zone combined and then set pipe to cover to the rubble zone. The second is motivated by an answered subsalt drilling window that contains settings casing and close to the base of the salt as possible. Operations considerations. Before salt exit, the first is update the pore pressure below the salt based on BSP look ahead. Consider a BSP look ahead for exploration wells. The next is the SBM is the best for drilling fluid. The next is use the logging while drilling with sonic and pressure while drilling. Prepare for losses. Have a large loss circulation material peer ready. Consider drill up on flatter salt structure which appears to creep to the least number of drilling problems. And the last is exceeding the salt requires careful drillings. Drilling the rubble zone below salt. 1. In the rubble zone, there can be high pore pressure and very narrow drilling margin. The drilling margin can be as low as 0.2 pounds per gallon. The first is the control the drill until the first porous formation is encountered. Watch out for the pressure regression, which can cause several losses. Flow check each drilling break. Continue to maintain a baseline for drilling fluid flow back. 2. ECD equivalent circulation density management. Break circulation slowly when tripping at certain intervals. In some cases, the mud weight is quite close to pore pressure. It may become necessary to pump out of the hole. The next is controlled drilling practices. Rope control is important before and just after salt exit. Determine the optimal RPM WOP and maintain both parameters as constant while drilling. 4. Drilling diagnostic. Monitor caving rate and type, radial torque and pickup weight, so the images of wellbore, and in some cases intermittent caving arrives at surface. And 5. Wellbore stability. A whole collapse in rubble zone is usually massive. 15 stability is not always useful. The sediments sometimes have no interesting streak, and fractures between rock fragments can be permeable. And finally, we have tips for diagnostic. 6. Drilling losses. At the first sign of losses, reduce the pop rate and pickup. Pull back to shield and allow the hole to stabilize. 7. Drilling fluids. SBM is more cost effective in the long run. 8. Casing design and setting depth. drilling as deep as possible below the salt, and closely monitor pressure regression and set the casing at least 100 feet in the regression zone. And the last is 17. In principle, try to extend cement coverage as long as possible. However, the limiting factor is the fracture gradient below the salt.